No, I'm in.
Hi, Al. Welcome.
Oh yeah, I can do this. Wish I got the USB one.
Maybe you can turn it on.
Yeah. It's not very wide.
Turn off.
Yeah. It's not very wide. Okay.
So did you read the material in terms of the program as providing questions?
Turning on, it's showing like waiting or something. But one more.
Is stuff showing waiting?
Yeah.
Okay. Let's hope for the best. Maybe could we call this guy? We're just here waiting for the data projector to start. Okay, the data projector is starting. Good morning, everyone.
Good morning.
Good morning.
Do we have Toronto? Do you hear us in Toronto? Yes, Laval. I see Laval.
Yes, Laval.
All right. Toronto. I can't hear Toronto. Yes.
Yes.
All right, Thomas. Thanks. Okay, so let me take the Hangout to the main screen here. Okay, waiting for this. Okay, I think our data projector is coming up. So everyone, since we have
Switch the input post.
yeah, please do. Yeah, it's good.
That's good. No, not yet.
Not yet. Now it's good. All right. Okay. And are we sharing the desktop too? Share screen. Yeah, I'm looking for the PPT now. Shall we start, everyone?
Yes.
Yes, perfect. So, Al, are you there, Al?
Yes.
Yes.
Yeah. So do you want me to present the to do the course introduction?
Let's find, most of the students were there, last Friday. There were some that, weren't, but they had looked at the material we distributed ahead of time. So if you do, go quickly.
All right. I think we have new faces here at Waterloo, so maybe I'll do that. Welcome everyone. Those who were here on Friday for the other course. I think we're gonna review very quickly the same material we went through in terms of the course introduction. Those who are new, welcome to this course is on network softwareization and dedicated to network softwareization technologies and enablers. So in this quick presentation, I'm gonna quickly go through the presentation of the entire program. It's called it's an NSERC collaborative research and training program called CREATE, dedicated to network softwareization. It involves 4 universities, including the University of Waterloo. You see the logos of the universities involved at the top of the slide. So ETS, École de Technologie Supérieure de Montréal, in Montreal, University Laval in Quebec City, University of Toronto, and here the University of Waterloo. So there are several professors involved here in this program. Mohamed Shrait, Nguyen Kim, and Mohamed Fatin Zani from ETS Montreal, Professor Rash from Laval, Alberto Leon Garcia from University of Toronto, along with Hari and Ali, and myself, Professor Butaba, here in the Computer Science School at the University of Waterloo. So I'm going to tell you a little bit about this CREATE program. The outline of this quick presentation is as follows. We'll start briefly introducing what network softwareization is, the overall program objectives, the elements of this program, including the courses, hence this course today, and industry partner involvement in this program. So first, what is network softwareization? Is a new concept that is expected to revolutionize how networks are designed and operated, making them more programmable and more flexible and easier to manage, and as well as to allow for faster innovation, deliver services and application with greater agility and lower cost. So there are two expressions of the network softwareization. One already very widely known and deployed under the name software-defined networking. Software-defined networking, or SDN for short, enables fast innovation by making the network programmable. And for those who attended the last class, we discussed the main principles underlying the SDN. One of them is the decoupling of the data and the control plane, and allowing for easier programmability of the data plane as well as the control plane, which is implemented in software as a logically centralized server. So together, these concepts in SDN allow for greater responsiveness, security, efficiency, and cost effectiveness, and many of these will be addressed throughout the courses. Another very important concept or expression on network softwareization is network function virtualization. And the idea here is to replace traditional hardware middle boxes, such as load balancers, firewalls, and Trojan detection systems, which are widely deployed in any enterprise or ISP network, and replacing these hardware middle boxes and flexible hardware middle boxes with software appliances running on in virtual machines or containers on commodity hardware, on commodity servers. And this reduces significantly capital and operational expenditures of network providers. Clouds are becoming a very important component of any modern network architecture, and cloud is also covered in this program, in particular the management of cloud resources in support of network services. So very important to know is that all network operators, or the extreme majority of network operators worldwide, are embracing this network softwareization and moving their networks to include more SDN and NFV and clouds. And because of that, they are in high demand for graduates with these new skills, graduates who master the technologies underlying network softwareization. So as I mentioned, these courses are offered as part of an NSERC program. So most of you are familiar with NSERC. NSERC is the Natural Science and Engineering Research Council. It's a federal government funding agency. And NSERC funded the CREATE program for these 4 universities I mentioned before. And the objectives of this program, as approved, is to train graduate engineers to help Canadian and computer scientists, by the way, more so computer scientists, I would say, in order to help Canadian industry in the fundamental transformation that is being witnessed as part of this network softwareization movement. So this program will provide open and online education and training materials to introduce network softwareization, SDN, NFV, and cloud architectures. And for those who already signed on Piazza, you have received the first set of video recorded lecture for at least the other course, and a lot of the material will be provided online. And as you could tell, this course is also offered simultaneously in all 4 universities and throughout the term. So the graduate students that are targeted by this NSERC CREATE program are course-based and research-based masters, as well as PhD students. I mentioned before there is an industry stream where the students will participate in internships in the industrial with the industrial partners. What are the program elements? 2 courses are planned as part of the Network Softwareization CREATE program. One is dedicated to the principles and foundations of network softwareization. This one takes place every Friday from 9 to 12 p.m. So focusing mostly on the theory and design principles of SDN, NFV, and whatnot. And the second course, which is taking place every Monday from 12 to 3 p.m. or 2:50 p.m., is focusing on the is dedicated to the technologies and enablers of network softwareization, and the main goal is to allow you to develop the needed software skills in network softwareization, to basically have hands-on experience with all these technologies in SDN, NFV, and whatnot. So the courses are offered by experts in these areas in all 4 universities. The first part is provided by the University of Waterloo, and then as we move throughout the term, other professors from other universities will cover the other components of the courses. And as I mentioned, a very important focus of the course is hands-on experience with technologies, specifically as part of the course, this course today, using various state-of-the-art research test beds developed by the partners in this same program in previous projects. There is also research as part of this program on SDN, NFV, network management, cloud architectures, and internship in the industry. Okay. In addition to that, we plan also to provide the opportunity for students for training in soft skills or professional skills, including teamwork, communications, and whatnot, in order to facilitate the transition to industry for those that will have such career. So as I mentioned, 2 courses. The first one is dedicated to the principles and foundation of network softwareization. It's organized into 4 parts. The first part has already started, is focused on software-defined networking, and we had the first lecture on Friday. and will continue throughout the term. It's organized into 3 main parts. The first one, an introduction to SDN in week 1, then a detailed presentation of SDN data, control planes, and APIs, week 2, and the third week will be dedicated to the study of network virtualization, a related concept to network softwareization. The second part, which will be provided by Professor Rash at University of Laval, is focused on wireless and optical SDN. Among the topics covered, there is 5G front-haul requirements for 5G mobile telecom networks, the trends in multi-carrier optical physical layer, and spatial multiplexing. The third part will be provided by ATS in Montreal, and it's focused on clouds and cloud resource management. It's also organized into 3 parts. The first one to introduce cloud computing. The second part is dedicated to data analytics, and the third part will cover energy efficient and sustainable management of clouds. The fourth and last part of the first module is dedicated to network function virtualization and orchestration, and will be provided by University of Toronto, Professor Alberto Rein Garcia, and will cover programmable networks, network function virtualization, and a number of hot application areas, the Internet of Things, smart cities, and other 5th-generation mobile network use cases. So one thing that is worth noting is that the courses will be provided in a flipped mode, in that you will receive the video recorded lectures prior to class, and then when you come to class, the class will be dedicated to interactive sessions, questions and answers, as well as quizzes based on the pre-recorded video that you will receive before coming to class. The second course, starting today, is, as I mentioned, focused on the technologies and enablers of network softwareization, also divided into 4 parts, exactly the same 4 parts that we have seen before, except that in this course will be more on hands-on experience with the various technologies and labs for the most part. So for the SDN data plane, Open vSwitch and Mininet tutorials and labs will be provided. For the SDN control plane, one example controller will be studied, specifically ONOS. And for network virtualization, look at Flowvisor and other virtualization technologies, notably OVX. For the second part, there will be tutorials and exercises and potentially labs in the area of software, wireless SDN and optical SDN. For the third part, there will be labs with OpenStack, a very popular platform for cloud resource management, as well as workload characterization and prediction, and finally a tutorial on green ICT, that is the sustainable management of information and communication technologies, notably cloud infrastructures. In the fourth part, as part of this course, the labs will concern service orchestration and chaining. That is the chaining of virtualized network functions that replace middle boxes as I mentioned before. The federation of environment for providing these chain services end-to-end, and an IoT applications lab. So I mentioned internships. There are 2 types of internships, internships in the industry and an internship in a research lab, one of the 4 research labs across the 4 universities. So there is an application process for those eligible students. In order to be eligible for any of these, you are expected to take both courses, the theory course as well as the practice course. For the research fellowships, the application has to go to, if you are from the University of, say, Toronto, your application should go to the professor in charge at the University of Toronto. As I mentioned, there is also placement in the industry as soon as next term, starting in May, for those eligible students. there will be a topic for the internship that is decided in conjunction with the industry partners. Both the fellowships and the industry internships are funded, by the way, and they cover a period of 1 internship or 2 successive internships from 4 to 8 months, depending on the case. So obviously there could be more applications than slots available, and there is a selection process that will take place for both the research fellowships and the industry and internships. I mentioned professional skills that will be also training in professional skills that will be provided here, and that's mostly relying on NITACs, which is a funding agency that support student scholarships, among others. So there are 9 days of such training, covering, among other things, career professionalism, communication skills, presentation skills, teamwork, project management, entrepreneurship, and intellectual property. For tracking student progress, I mentioned a prerequisite for the funding, both for the internship or the fellowship. You have to take the 2 core courses. You have also to do the professional skills, and obviously you have to succeed in the two courses. And in order to succeed in the courses, there is a requirement that for the grading of the courses that involve class participation, which is worth 10%, quizzes for the theory course that are worth 40% of the course grade, as well as a project that is worth 50% of the overall course grade. For this technology and enablers, for this practice course, there is also a class participation worth 10% of the overall mark, and lab exercises that are worth 40% of the class of the course mark, and finally a project as well that is worth 50% of the overall mark. So there are a number of industry partners that are already lined up to partner in this as partners in this CREATE program, and these will be industry partners will be receptors, for example, for the industry internships. They include very important companies that you'll know of: Ericsson, TELUS, Bell Canada, Sienna, IBM Canada, and others. All right, so that was it for my quick presentation of the course of the CREATE program, and as well as the content of the courses. I'm happy to take, or we're happy throughout the 4 universities to take any questions you may have. Yes.
I'm wondering about overlay networks. It's like software-defined networking enabler for overlay. A lot of different things.
Oh, I have the question I have here. Let me repeat that for others. So the question is whether overlay network is whether overlay networks are enabled by software-defined networks, or it is something else. So overlay networks is mostly application layer networks, right? So they're deployed at the application layer. They're sort of virtual networks that are easy to create at the application layer, because we can do everything in the user space, right, at the application layer, unlike the underlying layers of the protocol stack. Whether SDN can be used in support of overlay networks, I would say there is nothing that prevents that from happening. You can have software switches deployed, and the routing in the overlay that is governed by or the traffic is steered using SDN in the overlay, at the application layer in an overlay network. Although this is, in my opinion, not really the most significant area where SDN can be useful. So SDN is more proposed in order to program the data plane, the hardware that actually forwards the traffic in the network. But there is nothing that you can still apply the same principles for traffic routing, for example, at the application layer. Any other question? Here in None, I think we can. I think the program presentation is over, and Am I hearing something somewhere?
No.
No? We're good?
Yeah, I think the presentation is done, the overall, and now you can move to the lab part of at Waterloo.
Okay, so I think we're gonna maybe switch now equipment so we can set up the. So just regarding the lecture today, obviously this is gonna be a lab dedicated to SDN, mostly Mininet, which is a very popular network emulator that allows you to emulate SDN networks, to deploy a network topology of SDN switches and a controller that controls the traffic forwarding in this network. I believe everybody received the information on how to download the virtual machine for that is needed for the lab today, and you all came with a laptop for that. Everybody's ready? Yeah, so we will switch here equipment at the University of Waterloo so we can start the lab as soon as possible.
We can.
Kim.
Yes.
Shihab is telling me that he didn't receive the invitation for Google Hangout. So everyone, I'm gonna disconnect for a minute and we're gonna set up the other computer.
Yeah, it's recorded.
Yeah, back to that.
Huh? That was distributed, so that's why we decided that with the. All of you should send me your email address for email and we'll actually be there and we'll see all of that.
Or passing it around right
pass
now.
it around. But still send me an email address.
What about
If you're taking that as well, send me a separate email.
Raouf?
Yeah, actually, there's a PDF just by the by
Raouf? I think he's.
He's speaking to another PCIS.
Should I tell him that he's not getting?
Yeah. Raouf,
Kim,
is Shihab around?
is he's here, but he's not getting the invitation.
I already
Okay.
sent.
No, but yeah, Kim just sent an invitation a couple of minutes ago. So fine.
Okay, let's. Is okay? You got the invitation?
I got the
Okay, he received the invitation, so hopefully coming soon.
And here, Raouf, here we have Tuan, who will be the moderator, the TA moderator.
Just.
Perfect.
Hello, Professor.
Hello, Tian.
This is Al.
This is Shihab.
Hello? Can everyone hear me clearly? Hello? So can everyone see my screen?
Yes.
Yes.
So hello everyone, my name is Shihab. I can hear my voice actually. There's an echo, yeah.
We have a strong echo.
Yeah, there is a strong echo here also.
Yeah. So I already sent a post on Piazza yesterday regarding setting up the PM. Wow. The echo is like very bad. Yeah, there's the. Then you cannot hear anything from here. Like this speaker will not hear. That's okay. That's okay.
Because they can hear you there.
Okay. Is there still echo? There is. It's less this time. Okay, let me just continue. Yeah, there is no echo now. Yeah, okay. So, all right, so continue with the lab today. So I guess at this point, everyone has the VM set up. And I also posted the lab notes. So the slides you're seeing right now, they're also posted on Piazza. So you can also use that on your laptops as well. Now, the credentials for the VM, again, it's in the slides, just in case it is required, but you won't need any credentials to log into the VM. Just only when we're doing super user operations, we'll use the credentials. So before starting the lab itself, I'll give a quick primer to SDN for those like who haven't attended the first lecture. Like a quick introduction to what SDN is, and then from there we'll move forward. First of all, we look at traditional networks. So traditional networks has what is known as a distributed and integrated control plane. So each device in a network has integrated inside the device. So distributed routing algorithm or forwarding algorithm. Now, in contrast to so for instance, here in this example, if you look at like a traditional network, so each of the router in the network, they maintain a global view. They try to maintain a global view of the network, and to do that, they run communicate with each other, exchange messages between each other, and in this way, at the end, each router has a global view of the network, and based on this global view, they take routing decisions and whatnot. Now, this control that builds this global view and computes the routing decision, this control is part of each device. So each device has its own control and is distributed across the network. So that's how traditional networks work. Now, in contrast, in SDN, so there are two main concepts. The first is the separation between control and forwarding. So the control is not built into the device itself, it is taken out of the device. And a logically centralized control. So in contrast to distributed control that we saw in SDN, like traditional networks, control is implemented as a central software, a logically central software.
Sorry,
That is deployed in a server or a cluster of servers, which controls the devices, the network devices. So the network devices, there is a protocol that the network devices use to talk with the controller, and the controller decides on how the packets will be forwarded in the network, what would happen if some links fail, what would happen if the status of utilization changes and whatnot. So everything is decided in this centralized control plane or centralized software. And the centralized controller then programs the devices to determine the forwarding behavior of the network. So this control is now separated from the devices. It's not built into the devices anymore, and it is logically centralized. So these are the key principles of SDN. So as we can see, so there is a separate data plane that is forwarding the packets. There is a separate control plane that is deciding on how the network should behave. And on top of this control plane, we can now have multiple applications that leverages the view, the global view that is available at the control plane. So, given that, for the remainder of the lab sessions, we'll focus on each of the planes and what are the different technologies that are available on each of the planes and gain experience with different technologies. So this week is the first week. We'll look at data plane technologies. So our focus will be on OpenP switch, which is a software switch, a software switch for SDN. And we'll also look at MiniNet. So MiniNet is a network emulator, because to experiment with networks, somehow we have to build a network, right? So MiniNet will emulate the network for us. So these are the two things we'll focus on today. And then on our next week, that's week 2, we'll look at control plane. So as an example controller, we'll look at Open Network Operating System Controller, or ONOS for short. And on the third week, we'll see an example of this combination of control plane and data plane, how they're used in network virtualization, how we can do network virtualization in SDN by using a combination of all these things. And for that, we look at 2 different technologies. So Flowvisor, this is one of the early works in SDN for network virtualization, and more recent tool, Open Vertex, or OVX for short. Now, so as we have said earlier, so SDN separates this control plane and the data forwarding plane, right? And there is a way for the control plane to talk to the data forwarding plane. There is a protocol for that. Till now, there is no standard protocol. Oh, can everyone hear me clearly, like at other schools?
Shihaber, can you please speak slowly, because there is some problem with voice quality from here and from Total.
Sorry, can you please repeat? I think we were like muted.
Yes. Can you please speak slowly?
Okay, all right. All right, thanks. So, okay, so getting back to the lab. So as we discussed earlier, so there is a separation between the control plane and data plane in SDN, and since there is a separation, there should be some way for the control plane and the data plane to communicate with each other, right? There has to be a protocol for that. Now, OpenFlow is one such protocol that allows this kind of communication between the control and data plane. I'm saying one such because there is no standard per se in this domain. This is to some extent a de facto standard, but not necessarily it is the standard in the domain. So different vendors, for instance, Cisco or Juniper, they have their own incarnation of a protocol for communication between control and data plane. But regardless of that, OpenFlow kind of became the most popular one and is the most adopted one by the vendors till now. So what OpenFlow, according to OpenFlow protocol, the way control and data plane works is, so in the data plane that is forwarding the packets, there is a component called an OpenFlow agent with the controllers or the control plane itself. So, and there is a controller, and there are like a number of controllers out there. For instance, Knox, that was kind of the first OpenFlow enabled controller, which written in C. There was Fox, which is Knox implemented in Python, similar functionality, and so on and so forth. So these controllers, they also implement this OpenFlow protocol at their end to communicate with the switcher. So this communication between this controller and the OpenFlow agent, this API, it is called a southbound API. Look at the picture. This kind of points to the geographical south, as opposed to the northbound API, which points to the geographical north. So the northbound API is for higher level application development. So it is the control plane's API for writing control applications. Now, what exactly is a control application? An application that can perform operations on the network by leveraging the features provided by a control plane. The traffic engineering application that always tries to ensure that the link utilizations are balanced. So it can leverage the statistics and counters provided, made available through the control plane APIs. Use those, perform its own, run its own algorithms. Traffics, tell the controller that, hey, reroute the traffic in this way to make sure that the link utilizations are balanced. So this is just an example of a control application. Any questions so far? From other schools? So that's one of the phases of OpenFlow, that it is like a protocol that enables this communication between the separated control plane and data plane. Specifies gives one specification of a switch that is SDN enabled. Because if you think about traditional networks, definitely there were hardware specifications, right? Hardware has some sort of tables that stores IP prefixes. There is a lookup operation on the IP prefixes. Based on the lookup operation, we determine where the packet is going to go. Right? So there is a structure as to the switch. Now, when we move to SDN, definitely we're taking the control part out of the switch. Definitely there is some other part that has to be defined. OpenFlow also specifies one possible definition of this data path for SDN. Combination of these communication protocols between control plane and data plane, and also at the same time it specifies how the data path should look like for this kind of operations to be supported. So OpenFlow provides this match action abstraction for the switches. For a switch to be supported by OpenFlow, it should support something like match on the packet headers. Based on that, take some action. So an OpenFlow switch supports some interfaces, like hardware interfaces, where it receives the packets or sends packets out. So when it receives packets on one of the interfaces, it takes a packet, maintains an internal table where it can match against some values of packet headers, matches in the internal table, and if there is a match found, there is an action corresponding to the match. So the action can be forward the packet to port X. Right? So say for instance, it receives a packet on port 1, finds a match in the internal table that, okay, if the TCP destination is port 80, then forward it to hardware interface port 2. This is an example of a match action. Now, the match can be performed on a number of header fields as defined by OpenFlow specification. For instance, it can be source destination IP address, it can be the layer 2 MAC address, it can be layer 4 TCP UDP port numbers, it can be some encapsulation header fields, for instance, like VLAN tag, GRE tag, so on and so forth. And also this header, these matches, they can be like an exact match that the match table specifies that, okay, this header, it should have exactly this value, or it can be a wildcard match saying that, okay, there can be any value in this header field. So both type of matches are supported by OpenFlow. So this is an example of how this match or this like entries in a flow table, they're organized. So as we have said before, there is a rule. There's a rule that defines how a match should be performed. There's an action that says what should be done when a match is found. And associated with these rules and actions, there are some statistics saying that, okay, how many packets have matched this rule, how many bytes have matched this rule, so on and so forth. Now, if we look into the rule, so this is just like a simplified example of what can be in like a match rule, as I said before, but there can be many more fields. So for instance, OpenFlow 1.4, it defines 41 possible match fields that can be actually matched in a rule. So this is an example here that is showing like one example rule. For instance, saying that there can be anything in the first 5 fields. So this is a wildcard match. However, there has to be a specific value in TCP destination port. If any packet matches this pattern or this rule, then it should be forwarded to port 4 of the switch. Okay. So this is just an example of like this match and action. Any questions so far? Very good. To other schools? So the others, I can see the other schools are muted. So I don't know if anyone is asking questions. I cannot hear them. We're good. Okay. Assuming we're good, moving on. All right, so that was the description of how the switches or the data path is defined as per OpenFlow specification. Now the OpenFlow protocol itself. So a quick overview on what are the different protocol messages, what are the sequence of operations that that is supported in OpenFlow. So first of all, say we have this OpenFlow switch. As we have seen earlier, it supports this kind of match action primitive. If there is a match on the packet header and in one of the rules in the flow table entry, then some action is taken. However, to start with, this flow table is empty. It is programmed by the controller. It is so OpenFlow, according to OpenFlow specification, this is a reactive approach. Reactive in the sense that initially switches start with nothing. As packets arrive, the flow table gets populated over time. How it is populated? So, say for instance, there is an OpenFlow switch like this. It receives a packet over a port, from ingress port, and the packet goes to the flow table. There is nothing in the flow table, so there is no match, right? Miss event. When there is a flow table miss event, the switch sends a message to the controller called a packetting message, saying that, hey, I got a new packet that didn't match any of the flow tables. What should I do with it? First. Now, the controller, it receives a packaging message. The switch also includes a part of the header in the packaging message, so the controller can decide on how to route this packet. It goes to the controller. Then the controller computes the route for this packet, looks at different fields based on the algorithm that is implemented in the controller, the policies that are implemented in the controller. It figures out, okay, this will be the path for the packet to be routed along the network. Controller goes to every switch and installs a flow table entry in every switch. Right? This is how the controller programs the switches with flow table entries. And for that, the controller uses these two messages: a flow mod message, a packet out message. So a flow mod message tells the switch that this is a new flow entry, install it on your flow table. So new entry is installed on the flow table. And packet out message tells the switch that now let the packet go out of your out of the buffers. So a rule is installed, then the packet that was waiting because we didn't find any match for the packet yet, that is matched in the flow table, and then when the controller receives this packet out, the packet is matched on the flow table, and based on the match, it is sent out on one of the ports. So this is the most basic operation of an OpenFlow switch. Starts empty, receives a packet, doesn't find anything, doesn't find any match, requests the controller that how should I forward the packet. Controller decides, sends a flow mod and packet out, and then the switch knows how to forward the packet to the network. Right? So apart from this most basic operation, OpenFlow definitely supports a lot more other operations. For instance, it allows the controller to query the switch about what kind of features are supported on the switch, the different counter values inside the switch. For instance, the counter values associated with the ports itself, the counter values associated with the flow table entries, so on and so forth. So, and again, like definitely there are like more messages defined in the OpenFlow switch specification and controller to switch protocol. We're all good. Other schools, any questions?
We are good here. Yes.
Okay. All right. Thanks. So now moving on. So far we have seen like examples of how OpenFlow works, right? OpenFlow defines a switch. There is also a protocol for switch to controller communication. Now, OpenVSwitch, it was like it started as like a reference implementation of an OpenFlow switch. Because when the first time the OpenFlow protocol was defined and the switch architecture was defined, we needed a reference. There was a requirement for a reference implementation. So Open Virtual Switch started as a reference implementation, but now it has become like a production grade virtual switch, software virtual switch. Virtual switch in the sense that it's not really a hardware device, it's a software switch that we can run on any commodity Linux machine. As is, it has two separate modules. It has a kernel module that resides in Linux kernel, and that actually performs the forwarding. Think about a Linux machine that has the networking stack implemented in the kernel. It receives some packets. We are using Open vSwitch to forward packets. Kernel module, it contains the flow table entries, and forwards it on another interface. And there is a user space module which communicates with the controller, implements the open protocol, communicates with the controller, and installs the rules inside this kernel module for packet matching. And definitely, there is a requirement for a remote controller. So the remote controller connects with Open vSwitch and like an instance of Open vSwitch and can configure the flow table entries in the Open vSwitch. So again, like for details about the internal architecture of Open vSwitch, there is a paper. I think I put a reference to the paper here. If anyone is interested, you can have a look. Now, for the subsequent labs, we'll use Open vSwitch for our reference data path. We'll use the CLI, Open vSwitch CLI, to see, okay, how can we install a flow rule inside the switch? How can we see the different statistics inside the switch? And how can we do these operations on a switch, so on and so forth. So there are two CLI tools for Open vSwitch that we'll be using. The first one is OVS VSCTL, or Virtual Switch Control, which is used to create instances of more switches. And there is another tool called OVS OFCTL, or Open Flow Control for short, which will be used to manipulate like individual switch instances, right? For instance, like adding a flow entry in a switch. So this will be done through OVS OFCTL. Now, before we can use all these things, what we need is a network, right? A network to work with. But how do we get like a network set up and working and start working on it? For that, we'll use Mininet. So Mininet is an emulator for SDN. Right? So again, it will emulate a software-defined network using Open vSwitch and Linux network namespaces. So with Mininet, what we can do is we can deploy, and the network topology can contain switches connected by links. We can specify the bandwidth, delay, all these parameters on the links. Hosts connected to the switches as well. And for the host, we can limit the CPU uses of the host, and also control the bandwidth that connects the link between a host and the switch, and so on. So Mininet can emulate a whole network in a single machine. So we'll be using the virtual machine we have to emulate networks using Mininet. So even there is a port for Mininet for Raspberry Pis. Anyone is interested and has a Raspberry Pi, can download the port, the Raspberry Pi port of Mininet, and do the emulation there as well. Now, a quick under the hood look at Mininet. So in Mininet, as I said before, we have these two concepts of switches and hosts. So a switch, now traditionally, when we use the term switch, it means a layer 2 forwarding device. It forwards based on layer 2 MAC addresses. But in OpenFlow, the notion of, although we use the term switch, but the notion of switch has been extended beyond layer 2. Beyond layer 2 to all the match fields that is supported by OpenFlow. So an OpenFlow switch is essentially something that can like perform all this match action operation according to OpenFlow specification. So the way switches are created in Mininet is, so OVS, or Open vSwitch, it allows us to create bridge instances. Bridge is a different name for a switch. So we create bridge instances using Open vSwitch VSCTL, or Virtual Switch Control. Create links between bridge instances, add ports to the bridge instances, and connect the links on the ports. So this is how Mininet works. And for hosts, Mininet deploys actually processes which are contained within a separate network namespace. So a network namespace in Linux allows creation of hosts who has different views of the network. So, for instance, if I have two different network interfaces and put two different virtual interfaces inside the namespaces, these namespaces will not be able to see each other's interfaces, routing tables, so on and so forth. So, if we just execute two different hosts spaces, they kind of act as two different hosts on a network who has different view, who has their own networking stack. Not full-fledged, to some extent limited, but still, like for our work, that's okay for now. All right. So now let's start up the VM, and so everyone can see my virtual machine. Other schools, like they can see my virtual machine as well. Yes.
Yes.
Yes. Okay. All right. All right. So Mininet has already been installed. So Mininet has already been installed on the VM, so we don't need to go through the installation process. But just in case someone wants to install it on some other machine, the command is given in the slide. So let's move to slide 15. Let's start Mininet without anything first. The way to run it is, so first of all, we have to run Mininet as a super user, since it will be doing operations like creating these bridges and whatnot. So it has to be run in super user mode. So let's start Mininet first without any options. So if we start Mininet without any option, it will deploy a very basic network. The network will have one switch and two hosts connected with the switch. And the links that is connecting the host and the switch, there is no limitations on the links, right? So it's not bandwidth limited, there is no emulated delay or anything. Now, so when you start Mininet, there is a CLI to perform different operations on the switches and hosts. So for instance, let's run some basic commands. The first one, if we run this command node, so can everyone see here, like in the class, the projector, the end, the bottom. So if we run this command node, so node will actually show what are the nodes available in the current network that is being emulated, right? So now, usually switches are prefixed by S, hosts are prefixed by H, and there is a controller node prefixed by C. When we run Mininet without any option, it deploys a default controller to work with the switch, so that it can install these forwarding entries inside the switches, and the switch can work, right? We can send some traffic in the network. So let's try another command from the CLI called net. So net will actually show how a view of the network that is deployed by Mininet, right? So let's have a look at this row, for instance. So what this row is saying is that there is a host H1, and there is actually a link from H1 to somewhere else. So the link has two endpoints, of course, right? There is a endpoint to H1, and that is the first part separated by this colon. So this interface is the host's interface that is connected to the switch, and the other interface is the switch interface where this host is connected to, right? So similarly, if we look at the other host, it has a similar entry, right? What interface of the host is connected to what interface of the switch? Similarly, the switch has multiple interfaces, and of course, 2 links are connected to the switch, and we can see the specification here as well, right? So the switch is connected to what other interface on the other endpoint. So the net shows like a quick view of how the network is, right? The questions? So far, so good? All right. So let's do a dump. So a dump shows a bit more detailed information on the hosts and the switches, right? So what it's showing is that, okay, we have 2 hosts here. We haven't specified anything, so meaning it has deployed 2 hosts. Shows the IP addresses of the hosts, and also shows the process ID of the hosts, because as we said before, the hosts are emulated hosts. They are not actual like machines or containers connected with these emulated switch. Basically, they are processes inside the networking space. So we can see the PID from here, and we can actually do like more advanced work by taking the PID and run some other Linux utility to perform operations on it. Right? For instance, limit the CPU uses of this particular process. Another tool to limit the CPU uses. That's just an example. Or pin this particular PID on a specific CPU. So we can get all the information from here. And we also have information on the controller. So just showing that, okay, what is the IP address of the controller? What is the TCP port this controller is listening to? Usually the controller maintains a TCP connection with the switches. So this is 6633 is the standard TCP port used by all the controllers. So these are all basic information on what is deployed and what is the different information. So what are the nodes that are deployed, what are the different interfaces present on the nodes, what are the IP addresses, PIDs, and so on and so forth, like all the information about the host and the network. So good. Any questions? Give it a try on your laptop. Here in the keyboard. No? So the question is the switch and controller. So yes, because the controller is running on the same machine. So this is at this machine. So what you can do is, even with Mininet, you can specify a remote controller. This is running on a different machine and also specify the IP. In that case, it's a different IP address. All right. Any questions from other schools? Okay. All right. So moving on. And am I going too fast, too slow? Is it okay? Question for everyone.
It's okay. It is just.
Okay. Okay. All right. Thank you. So then the next thing, the hosts, right? Now, as we said before, so each host, it has its own network namespace, and it is actually running as a process. So from Mininet CLI, we can actually run a Linux command inside a host. Right? It provides this interface to do that. So for instance, say we want to see the network configuration, the network interface configuration for host 1. We run something like, first we specify which host is our target host, like where we want to run the command, and then execute it. Right. So what happened here is, so we run this ifconfig interface config command on host 1. So it executed the command inside the host and showed us the output. So for instance, we can see the interface configuration for host 1, right? If you remember, like host 1 had one interface that was connected to switch 1, so we had seen the details of that interface. Similarly, if we do it for instance, host 2, just h2 ifconfig, we can see the interface configuration for host 2 here as well. In fact, let's run something different. Say we want to list the directories like in the root of the home folder of host 1. So h1 and then followed by the command we want to run in h1, right? So it shows us what is in the file system of h1. Similarly, h2, we run another same command, it would show us what is in the file system of h2. Now, Mininet does not isolate the host in different mount namespaces, so we will actually see the same content inside both of the file systems right now. But there is also this concept of mount namespace in Linux, where you can isolate the disk view of each process. So in that case, you can have actually separate views. But anyway, so this is just a way to show that it's possible to run custom commands inside the hosts. Let's run another command inside a host. Let's try to ping host 2 from host 1, right? So since we're trying to run ping from host 1, and then the command itself, so it started pinging. So host 1 is now pinging host 2. Control C to break it. Similarly, if we do the other way around, host 2 will start pinging host 1, right? So essentially, right now we have a network. Now we can actually do whatever we want with the host and the switches. And the ping, major latency, and so we're good up until now. Everyone on the same page. So everyone was able to run a command from one host and see the output on the virtual machine. Everyone, okay, all right. Try to respond in using something like yes or no. That helps me to better understand. Other schools, are we good?
Yes.
Okay, all right, thank you. Next. Now, Mininet has some built-in tools for diagnosis. For instance, say we have deployed a network. We want to check that the network has been deployed, the controller has been deployed, and everyone can actually talk to each other, right? So it has a tool called ping all. So ping all will actually do like all pair ping and show you the results. So if there is an issue with connectivity, say for instance, you forgot to deploy the controller, right? So then there is the controller. So everything is deployed to ping each other, right? The hosts will not be able to talk to each other. So this would show that. So there is a Mininet CLI called iPerf. So iPerf will pick two hosts and perform a bandwidth test in between the hosts. So for instance, I did iPerf here. So right now we have exactly two hosts. We don't have more than two hosts, right? Pick the two hosts and perform a bandwidth test in between these two hosts. And will show you the result of the bandwidth test, right? Now, iPerf by itself is a tool. We'll see later how we can separately deploy this tool among different hosts and tune the parameters of iPerf to send traffic at a specific rate and whatnot. So this is basic Mininet. We deployed the network, which is a very minimalistic network. We had one switch, two hosts. We were able to see the network interfaces, the information about the host. We're also able to run custom commands inside the host for now, right? And we also see basic diagnosis tools to see the connectivity and measure some very basic bandwidth tests in between hosts. Right? So let's first of all quit Mininet. It will clear up everything. Whatever it has deployed, it will delete all the switches and destroy all the host and the controllers. So what we'll do is we'll deploy using something like connected to each other, like similar to a line, and each to. So it allows you to specify like a type of topology that it supports, like a custom topology that it supports, and also some parameters to parameters related to the topology itself.
Tiago?
Which is linear space.
Hello?
Yes.
Can you
Yes.
check your network again? Since pretty difficult to hear you from BTS, and I think from the
sorry,
other.
can you cut off?
Do you hear me? Can you check your connection?
Can I check my what?
Okay, we can hear you now, because a couple of minutes ago we could not hear you clearly. Hello?
Hello?
Okay.
Hello? Yeah, I think the call got disconnected. Can you hear me now?
Okay, it's good now.
Okay, let me share. So can you see my screen?
No.
Okay, all right. Let me share my screen again. Just give me a second. Right.
Okay, it's okay now.
It's okay now? Okay,
Yeah.
all right. So let's get back to the VM and let's try to deploy a linear topology. So what we'll do?
About 5 minutes.
Sorry, I cannot hear you.
I said, could you back up about 5 minutes because we lost the audio, so we're not sure where you are.
Oh, okay. So what was the last thing you saw?
Ping all and
Ping all?
yeah.
Okay, all right. Okay, let me back it up a little bit. So I was at slide 17 when I did ping all. Okay, so were you able to follow till the end of like ping all and iPerf?
Yes.
Yes. Okay. All right. So what I was saying is we saw like a very basic topology deployed using Mininet. Now we're going to deploy something a bit more complex, step by step, like this from a very basic one. Now we'll deploy a linear topology, and then we'll try to deploy a tree topology, and after that we'll try to deploy a custom topology using Mininet Python API. So we'll go like progressively, step by step. So first of all, we'll use the built-in topologies supported by Mininet to deploy a linear topology. So Mininet has this option called Topo, and it supports a number of internal built-in topology types. So one of the type is linear. And if you specify a number here, for instance 4, it will actually deploy a linear topology of 4 switches. All right. So what we did here is deployed a linear topology of 4 switches, and as you can see here on my screen, it actually shows you what were the links that were added. So with each switch, we added a host as well. So for instance, H1, H2, H3, and H4, each of them are connected with the switch. Now let's try to see something like a ping response. Say for host 1, let's ping host 2, right? And stop the ping. And let's look at the results for a bit. So we have a topology, right? We deployed 4 hosts. We tried to ping the first 2 hosts. Now, if you look at the numbers here, right, at the end, we can see the round trip time for the ping as well. Right? And if you look closely at the round trip time, what we can see is there is actually a difference between round trip time for the first ping and the subsequent pings. Any idea why is that? Yes. Right. Right. Other schools, any idea why is that?
I think because it has to talk with the controller first.
Because of?
It has to talk with the controller when receiving the first packet.
Yes, yes, exactly. Exactly. That's the reason. So for each flow, right? For each traffic flow in the network between some source and destination, the first packet, it has to go to the controller for a path setup phase. I mean, okay, if there is already a flow table entry that can do the match, then we're good. But otherwise, it actually has to go to the first to the controller. The controller completes the path and installs the rule, right? And that's why the first packet usually experiences more delay compared to the subsequent packets, and that we can see here on the result of our RTT in P. Right, the first one has significantly more compared to the rest now let's try to ping the last one, the first host. From the first host, let's try to ping the last host. So from H1, let's try to ping the last one, H4. And let's stop here. Now, in this case, we still see the same thing, right? The first one, for the first one, the delay is definitely more compared to the other ones, right? But if we look at the results of these two separate sets of pings, so in the first one, we are pinging H2 from H1. The second one, we're pinging H4 from H1. Now, for the first packet, it's actually experiencing significantly more delay compared to the first set of pings. In the first case, our path was shorter, right? H1 and H2, there was just a single hop in between them. So the controller had to install rule on just two switches. One where it is the longest path between the source and destination, where the controller has to install its flow forwarding rule on more switches, right? And that takes more time. As long as all the forwarding rules are not installed, a packet cannot go to the destination. So the longer the path is, the more the delay will be. Any questions? So even if so, now if we deploy even a longer chain and try to send a packet from the first one to the last one, we'll see even more delay experienced by the first packet. So the delay will actually keep increasing as the network size grows. So that is actually one of the, because now think about it, this network is geographically distributed, wide area network, where the latency between even a single switch and the controller is already high. You have to do this path setup among multiple switches using a centralized controller. There will be a significant delay in path setup. So there are approaches to deploy multiple controllers, divide switches into zones to minimize delays, and so on and so forth. But those are separate research issues, so we'll not focus on that. But just to give you an idea that this is one of the major issues that was one of the major concerns of SDN, is the scalability of the control plane, especially this flow setup issues. Any questions? Yes, go ahead. So there was a question here in Waterloo that why doesn't the controller send install the rule simultaneously on all the switches? It depends on the controller implementation. The controller can actually do that. Yes, in this reference implementation, it doesn't, but it can do that. But most of the controllers, they operate in a sequential mode. Install the rules sequentially along the switches. Again, that was an implementation and engineering issue that has been discussed in literature. Feel free to have it. Any more questions? From other schools, any questions?
No from it, yes.
Okay, all right. So moving on. So let's let's close this instance of Mininet. Right. And let's look at, oh, sorry. Okay, so let's close the instance of Mininet and quickly have a look at what are the options Mininet provides, right? Especially for the topology. So what we do is we run this Mininet with -h option. So it will show us the different options that we can run. We can do with Mininet. And let's have a look at this row called topo. So as I said before, like one of the options that we use right now is linear, right? So linear deploys a linear topology. Again, there are other options. For instance, minimal topology, which is the one Mininet deploys for default. Now we'll actually deploy a tree topology. Right? So a tree topology it's a hierarchical topology where we have a root node connected with more nodes, where each node acts as a root. From there, we can like further like expand up until we reach a certain level. Let's try to deploy a small tree topology with Mininet. So with tree, we can specify a few parameters. So for instance, there is a depth parameter that determines how far the tree will grow, and there is a fan out parameter that determines the breadth of the tree. So fan out would be how many more nodes that are connected to like a switch in a tree. So let's try to deploy this example here. So deploying a tree, it's not a very like a big tree. So there has a depth of 2 and a fan out of 2. This means that every switch is connected to 2 other switches. All right. So it deployed 3 switches, S1, S2, S3, where switches S2 and S3 they are connected to S1, right? So like a tree. And then with each leaf node, which are the switches S2 and S3, we have more hosts connected with it. So it's just a small tree with 1 root node, two more switches connected to the root node, and each leaf switch they have like 1 host connected to it. So this is just another example of a different type of topology we can deploy with Mininet. Now there are more. Go through the command like CLI references to have a look at more. So what now what we'll do is so far we have deployed these links without any properties, right? So we have deployed links, but we didn't really specify any bandwidth for the links or any delay for the links. So let's specify some bandwidth and delay for the links. So let's start to deploy topology which has like more properties. So quit from here. All right. So we go to our slide. So I'm on slide 17 right now for everyone's reference. Let me copy the command first and explaining it. Oops. Okay. All right. So we'll now deploy another linear topology. So the topo type is linear with 4 switches. All right. And what we want is that the links that will be deployed, they will have a bandwidth of 10 Mbps, 10 megabits per second. And there will be a delay of 5 milliseconds on the links, right? We need to specify another extra parameter when starting Mininet with this option -- link. With this option, we say what will be the type of the link. right? So by default, Mininet does not do anything with the link, right? The links are like default links with unlimited bandwidth and minimal delay. There is no emulated delay in that. There is a type of link called TC link. So TC stands for traffic control. So TC is essentially a Linux subsystem for emulating delay, limiting bandwidths on links. So internally, Mininet uses these TC commands to emulate all these things. And then we specify the parameters. So first, we specify the bandwidth of the link with the PW parameter. By default, the unit is megabits per second. And then we specify a delay parameter, which is the delay of the link. Now, when we deploy the network, lots of output. Essentially, what is showing that we deployed all the links and what were the delays and bandwidths of the links, right? It was deployed properly or not. From host 1, let's try to ping host 2. And let's have a look at the output. So again, the first RTT is higher compared to the other ones for obvious reasons. That there was a packet set of phase for that. Now for the other RTTs, so the way they're connected is that host 1 is connected to switch 1, switch 1 to switch 2, and switch 2 to host 2, right? So there are 3 links in between them. Now we set the delay for each link to 5 milliseconds. So the round trip would be approximately 30 milliseconds. And we can actually see that here as well, right? That's reflected in the results. Give it a try on your laptop. Like, try to deploy the network with emulated bandwidth and link, perform a ping, and see if you can see the result or not. Does it work for everyone? Even at other schools, are we at the same page? Everyone was able to deploy the network with emulated. Okay, got thumbs up from Toronto.
We have the same result. I have the same result. Only the
Okay, all right. So
only the first package just take about 60 milliseconds instead of 90.
Which is okay, because these are like transferred to the local interface, and it's not, delay is not really predictable sometimes. All right, so then the delay parameter works, right? And let's check the bandwidth then. So let's try to test the bandwidth between. Okay, let's just pick two hosts and let Mininet do the bandwidth test. So we set the bandwidth to 10 megabits per second. From the result, we should be able to see something that is close to 10, not exactly 10. This value is like a guideline. It doesn't exactly limit it to that value. It might be something sometimes less, sometimes more. And as we can see, the results from here, the bandwidth is somewhere close to 10 megabits per second, between 9 and 12 here. So we deployed a network with emulated bandwidth and delay, did some test, and it works, right? So the delay parameter works, the bandwidth parameter works as well. All right, so having said that, we have, so just to sync up with these slides, so we have covered up until slide number 19, and moving to slide 20 right now. So we can now deploy a network, right? With some topology, we can deploy a network. So since we have a network now, let's try to run some Open vSwitch CLI commands to see what is inside the switches, right? The floor tables and whatnot. So let's get back to the VM again. Let's keep the network running. I'm just opening another tab. So first, OVS, it keeps track of all the bridges or switches that we have deployed, right? So we have deployed 4 bridges, right, with linear topology. Let's try to see them. So what we'll do is we'll run these, we'll use this OVS virtual switch control or VSCTL, see what has been deployed and what are the ports and whatnot. So it takes this command called show as super user, and everyone should see and output something similar to this. A lot of output. Okay, let me run it again. Right. So yeah, everyone should be able to see and output something similar to this, where it will show like the details of every bridge. So for instance, it is showing now here the details of bridge S2. If you go down further, there are like details of other bridges as well. So if the first, so these parameters that I have highlighted right now, it shows that, okay, what is the controller that is controlling this particular switch instance? It will show the IP address and port number of the controller. Open vSwitch supports connection with multiple controllers. One is a master controller, one is a slave or backup controller. So you can see actually like multiple controllers listed for each bridge, or you can see just one controller listed as well, depending on what is running. So here Mininet by default deployed as many controllers as needed. So we are saying 2 here. If the connection to the controller is lost, the status will show here as well. It will also show what are the ports and interfaces and what are the types available of those ports here as well in this bridge specification. So, and this bridge control command, like the virtual switch control command, it can be used to actually create more bridges, right? So for instance, we have deployed 4 switches here, that is 4 bridges. But if you want to do that by yourself, say we want to deploy like custom topology by yourself without going through Mininet, we can create more bridges through here. The way we do that is we run virtual switch control with this subcommand called add bridge, add-br for short, and specify a name of the bridge. When we do that, it creates actually another bridge. And we can actually see that here as well. S5. Right, so we created this bridge by ourselves, right? S5. We haven't really specified anything for it, right? Whether it's controlled by controller, what it has other ports or not. So those are not showing here. But again, like when we want to deploy something with our own, like without going to Mininet, so this is the tool that we'll be using. All right. Now moving on. So now moving on, let's further zoom into the insights of like one single switch, switch 1, and see what is inside switch 1. So for that, we'll use this command called OVS OFCTL. So OFCTL is for open flow control. Now we said earlier, right, that every switch it has an open flow agent and that can talk open flow with an open flow control plane. So OVS OFCTL, although it's a CLI, but under the hood, it actually talks open flow. So when we execute some command using OFCTL, it creates those open flow messages and communicates with the switch over the control channel and sends those messages, gets the replies, and just displays it here. So this is like a manual control plane, right? It's not a software control plane, it's for a human CLI control plane. So let's run one command. So there's a command called show that will show us the summary of the switch. So for instance, we ran. Let me make the output more convenient. All right. So when we run this show command on this particular switch, it first shows the number of tables supported by the switch. Remember when we discussed about OpenFlow, we said that there are like flow tables supported by the switches. So OpenFlow actually allows multiple flow tables in the data frame. So there can be multiple flow tables. They can be chained together. Again, the details will be covered in the foundations class actually. We're not going through the details here. But when we run these OFCTL command, it will first show us how many tables are available in the switch that can be used. Then it also shows the different capabilities and actions supported by this particular switch instance as well. So for example, it's saying that, okay, here, the switch can support operations like it can output a packet to a port. It can modify the VLAN tag. It can strip a VLAN tag out of a packet, and so on and so forth. So OpenFlow specification defines a lot of actions, but not necessarily all of them are implemented in a particular switch implementation. So these actions are actually the ones that is supported by the switch, that is implemented in the switch. Similar to this OpenV switch, if this command is run on even in a hardware switch, it will show what actions are actually supported by that hardware switch itself. Maybe it can have something less, something more, something completely different than what we are seeing here right now. And also some switch capabilities, as in like whether the switch, for instance, in this case supports per flow statistics, per table statistics, so on and so forth. We can run the same command on the hardware. We can probably see different things or the same thing as we're seeing here, but it will show what exact capabilities are implemented by this particular data plane equipment. Not necessarily, maybe not all the things that is defined in the specification. And then description of the ports. So for the first switch, we actually had two physical ports. One port was connected to a host, and another port was connected to another switch, right? So it shows the speed of the link, speed of the ports, that is the speed of the links. Now, if you remember, we so if you remember, we did emulate the link capacities to limit it to 10 Gbps, right? When we deployed the network, we limited the link capacity to 10 Gbps. The port capability or the port speed here, it is actually showing 10,000 Mbps, which is like more than what we set the limit to. The thing is, the emulated bandwidth limitations, that is actually done by a separate subsystem than OpenV switch. So from OpenV switch's point of view, it still sees the port as a 10 Gbps port, but from Linux TC or the traffic control subsystem's point of view, it further reduces the rate of this particular interface to 10 megabits per second. So that is actually another layer that is acting after the packets are going out of this link. That is not part of this OpenV switch subsystem. That is part of a separate subsystem. That Mininet is kind of integrating all these subsystems together to provide us all the features. Any questions on that? Other schools, any questions? No? All right. So moving forward, so that was like the most basic operation. So we were able to see the insights, like the different capabilities of a switch and the port description and whatnot. So let's take a look at the flow table. To have a look at what exactly is in a flow table of a particular switch, there is a subcommand called dump flows. So what dump float will do is it will just print all the floatable entries that is currently present in that switch, right? Now, if you have been idle for a while and not running any traffic at all, when we dump flow, we'll see something like this. So there is no floatable entry, right? It really doesn't show anything. Because actually there is nothing in the flow table. The flow tables are empty. After a while, the entries in the flow table, they're evicted, they time out, they're evicted, and we don't see anything. Now, let's get back to our mininet window. Okay? And try to run a ping. So let's ping H2 from H1. Keep the ping running, and let's get back to the other window where we are seeing these statistics. Now let's try to dump the flows again. Now we can see actually a lot of output, right? Because there was no flow table entry, we started some traffic. Since there was no entry, there was a miss, the controller was communicated. Now the flow tables are populated, right? So the packets can actually go from source to destination. So if we look at the flow table entries, so just highlight one of the that properly. Okay, all right. So this highlighted part is actually one specific flow table entry, right? So the flow table inside switch 1, like S1, it has many entries because if you think about ping, it is going from one direction to the other, and also there is a reply coming back, right? So there has to be like separate flow table entries that is setting a path for both directions. And also, if you think about the network, when we are sending a packet to an IP address, there is an initial phase where there is an ARP or address resolution protocol phase that determines what is the MAC address for the IP address. Since the ARP tables are not populated, so of course there will be traffic for ARP queries as well. So we'll actually see different entries in the flow table that is actually handling different types of traffic, like these ARP entries, ARP traffic, the ICMP traffic, that is the ping, and also the reply. So the first one, so let's just have a look at what are the components present in the flow table entry. So it shows the identification of the table, which table this flow table entry belongs to. As we said before, there can be multiple tables, numbered from 0 to increasing order of like 0, 1, 2, 3, 4, and so on. So this is an entry in table 0. It shows some statistics about the flow table entry. For instance, how many packets and how many bytes matched this particular entry. So here it is just one packet with 42 bytes. Okay, all right. We'll see why. It shows an idle timeout. So idle timeout is a timeout value. So if the flow table entry is not matched in the past this many seconds, this entry will expire from the switch. Like it will not be in the switch anymore. So if I stop the traffic and stay idle for 60 seconds, this flow table entry will expire. But if I start the traffic within 60 seconds again, then definitely this entry will stay. If this entry will stay, it will not expire, right? And then what else we have? Then from here we can see a priority value. So a priority value actually is used for breaking ties when there are conflicting matches. Say for instance we have two flow table entries with match fields defined, but different priorities. But somehow the match fields they overlap with each other, right? So in that case, a packet can actually be matched with multiple flow table entries. When that happens, a priority value actually breaks the tie between multiple flow table entries, right? If the flow table entries are distinct, then the priority value doesn't make any difference at all. It really doesn't matter what's the priority value. Then we also have an entry for import. So import is the physical port number where the packet came from. It's an entry that is matching packets coming from port number 2 of this particular switch. Then there are some familiar fields, for instance, data link source, this DL source here. Then data link destination, the DL destination here. At the beginning, it is defining the type of data link layer protocol. The type of packet this data link layer protocol is encapsulating. So in this case, this entry is actually for ARP packets and ARP related fields in the table. And at the very end, we can see an action, right? So given that a packet matches all these values in a field, what should be the action taken on the packet? So the action in this case is output on port 1, right? That's the action. So that's how a flow table entry looks like. It has a bunch of fields that can be matched against the packet. When they are matched, there is an action at the end, right? And this action is one of the actions supported by this switch. Now, again, from the controller point of view, it can ask the switch to perform any action. But again, if the action is not supported, then the entry will not be installed on the switch because the switch does not support this particular action. So that's why the controller usually queries the switch about, okay, what are the actions supported by you? They tell me that through a request. Switch tells the controller that, hey, these are the actions that I can support, and the controller, like when it installs the rules, make sure that it does not install any rule that is not supported by the switch, right? So this is an example. Again, if you look at another flow table entry, for example, the third one, so this one is actually for an ICMP packet. So as you can see here at the rule part, it is specifying also the network source, network destination, these IP layer headers. The type is ICMP and whatnot, and forwarding the packet over. Right? Any questions on flow tables? And it was, yes, go ahead.
My question is how do I know the support action in the upper OBS suite?
Okay, so when we executed this command called show, right, OBS OFCTL show on a particular switch, it actually showed us the list of actions that is supported by this particular switch. Can you see that?
Yeah.
Yeah. So it shows the list of actions that is actually supported by this particular switch. Now, there is an OpenFlow message called feature request. So when the controller sends this feature request message to a switch, the switch replies with a feature reply message. So the feature reply message supported capabilities, the list of supported actions by that switch. So that's how the controller knows. Even when we're running this command at the under the hood, we're actually sending this feature request message to the switch. The switch is replying back with like a feature reply, like the set of features is supported, and basically it's just parsing and showing it here in the CLI. Does it answer your question?
Yeah, it is.
Yes. Okay. All right. Any questions from here? We're good. All right. So now moving on. All right. So all right. So far, what we have seen is that we can, like from the CLI, we're able to see the basic features of a particular switch. Again, we're able to see the what is in the like a flow tables. We can dump the flows in the flow tables of a particular switch. And again, like all these commands, not only they just run on virtual switches, they also run on the hardware switches as well. So let's see another command that will show us the port statistics of a switch. So let's take switch S1, for example. So the command is OVS OF control dump ports. So dump ports will dump the port, like print the port statistics of all the switches. So when we run the command, so not all the switches, sorry, all the ports of a particular switch. So when we run the command, it will show us, okay, how many packets were received on a particular port, how many bytes were included on all those packets, whether any packets were dropped, there was any framing error or any packet corruption, overflow of buffers, CRC errors, and so on and so forth. So when we run the command again, under the hood, it actually creates some overflow message called statistics request. Sends the message to the switch. The switch replies with a statistics reply. Request can also be used to query about very particular flows. Usually the controllers use that version of the message where they query about, okay, what is the utilization of this particular flow? What is the number of bytes matched with this particular flow? And in this way, we can actually figure out what is the portion a flow is consuming on a particular link, right? We can query the flows, get the bytes used over a period of time, and figure out, okay, what was the utilization of this flow of a link. So these are some of the features supported by OpenFlow. There are some more statistics messages. I'm not really going through the details of all of them, but this is just an example. All right, so far we have seen the insides of a switch. We have seen the like the flow tables of a switch and some basic statistics. The next step would be to manually add a flow entry in the switch, right? So what we'll do is we'll start with a network that doesn't have a controller, and then we will be the controller, the human controllers, who manually add an entry to the switch to make sure traffic can actually flow from one end to another. All right. So, do you want to take a break, or is everyone like keep going with the class, or do you want like a 5 or 10 minute break? Other schools, do you want a break?
Yeah.
Yeah. All right. So let's then convene at 2:15. So let's take a roughly 10 minute break, and let's reconvene at 2:15.
Okay. Okay.
All right, so let's reconvene our lab session now. And everyone can hear me, correct? Just checking if I muted my microphone and forgot or not. Okay, all right, good. All right, so now we'll try to manually add a flow table entry in a switch to make sure there is a valid path that can carry traffic between a source and a destination. So for that, let's deploy. Okay, let's stop the ping requests, quit the current network, and let's deploy a network where there is no controller. Okay, to do that, we're running mininet. Let's deploy a small topology. Let's deploy something like a single switch with 2 hosts, and okay. So what we're doing is we are deploying another mininet. Like with mininet, we're deploying another topology, but this time we're explicitly saying that there should not be any controller present in this network. So we're using these flag dash dash controller to none. Right? So this will deploy the network, but without any controller. And the topology type is single. So a single topology is essentially one switch and 2 hosts connected to that switch. So we have a very minimalistic network. And let's try to see. Since we don't have a controller, so we should not be able to send any traffic, correct? Let's run ping all, and it should fail. In this case, failure is success. Yes, it failed. So there is no controller. It was not able to set up any path. So ping failed. It was unable to send any packets at all. Now, let's get back to the other window and try to add a forwarding rule in the network. So what we'll do is, let's start a ping from H1 towards H2. So I think it will keep showing that our destination host is unreachable, which is perfectly fine. Let's go back to another window to add a flow rule inside switch S1 to make sure that we actually see like a ping response back here. All right. So let's get back here. So what we have right now is one single switch, right? It has two ports, port 1 and port 2. Host 1 is connected to port 1, host 2 is connected to port 2. The rule we'll put inside the switch is that host 1 is sending traffic on port. If there is any traffic on port 1, just send it to port 2. A very simple rule. Will not match on any other fields. Just to give an example, all right? And for that, we will use this OBS ofctl command, and help this subcommand add flow. Right? So with add flow, we can specify a signature of a flow or a match fields of a flow, followed by the action that should be taken for that flow. Right? I think I have an example on the slide. I'll just copy that to avoid any technical difficulties. So the flow here looks something like this. So I missed the thing here. Sorry about that. So what we're saying that add flow to switch S1, and the flow signature is, if it is coming from incoming port 1, then take this following action. The action is output on port 2. All right. Let's add the rule. It will ask for a password, and the rule should be added, right? We are still seeing destination host unreachable here, but let's check with dump flows if the rule was added or not. So the rule was added. So we have one rule in the switch that is saying that if there is a packet from port 1, then take the following action, output it on port 2. But then why are we not seeing any response here? Because there is a path, right? So we're sending packet from host 1 to host 2. We have a flow. So we have like a rule that is saying, if there is a packet from port 1, send it to port 2. Then why are we not seeing any response here? Any ideas? No reply. No reply. Yes. Yes. Because there is no reverse path setup, right? It's the ICMP message. So there has to be an ICMP to reply back. So let's set up the reverse path as well. So go back to the same command. So the reverse path would be, if there is a packet on incoming port 2, then output it on port 1. And okay, yes. And voila. So the path is set up. The packets are going back and forth in both directions, right? So when we executed these commands to add a flow to a switch, under the hood, what it did was it created this open flow message called flow mod or flow modification. So flow mod message tells the switch that modify your flow table and add this entry to this flow table, right? And we are also specifying what entry to add to the flow table, right? We are specifying the match fields, the action to be taken, and that entry is added to the flow table. So the path is set up, we can see traffic, and let's dump the flows and see. PSCTL, OFCTL. right? Oops, not me. So, floats. All right, so we have two flow entries describing two back and forth paths. You can see the number of packets and bytes and whatnot. There's a difference in number of packets because the delay of installing the rules. So definitely the later rule matched less number of packets, right? Yeah. So any questions? So was everyone able to do that on your virtual machine as well? Create a very simplistic network, set up the flow rules, and department setup that you can ping each other. The two hosts can ping each other. Did that work? In other schools, did that work?
Yes.
Yes. All right. I did not get any response from Toronto and Laval. Okay. All right. All right. So seems like it worked for everyone. Now moving on. So these are the different operations we can perform on an open flow enabled switch, right? We can. So essentially, this is showing how a wrapper around this open flow protocol can work. When the same functionalities are being done from a controller, we'll not be doing it from CLI. The controller will actually create the messages and send it to the switches. So our next lab session will be actually using a controller to do these things. Today we are working directly with the data path elements with the CLI, but then in our next session we'll try to do a similar stuff with a controller, like ONOS controller. But before that, one last thing for today is, so what we've seen so far is that we can create some built-in topologies using Mininet, right? So like split topology, linear topology, or maybe a very simplistic, like a single switch, two host topology. But what if we want to deploy something more customized? Say, for instance, we want to deploy network topology of a campus network. For instance, here in Waterloo, there is a campus network with the routers and switches and whatnot. We want to deploy a topology that looks like that. Mininet doesn't have that, correct? Mininet doesn't have built-in Waterloo topology or Toronto or ETS or Laval topology. So there is another way of creating custom topologies. So that is Mininet has Python API. So with the Python API, we can actually program the topology itself. We can specify the number of switches, number of hosts, the way the switches and hosts are connected to each other and whatnot. So we'll see an example of Mininet Python API and create a custom topology with that. And that will be the last thing for today. So let's get back to the slide. So on slide 24, there are resources on further details of the Mininet Python API. I mean, so there is an API reference available online that lists all the API function features and uses that you can possibly use. But right now, we'll just go through one example to deploy a custom topology and run some traffic inside the topology. Okay. So on slides 25 and 26, 25, 26, and 27, these three slides together, they contain actually one Python program. Just in case you're not very much familiar with Python, I'll try to go through, walk you through the program to make it easier for everyone. So at the beginning, what we have is a bunch of imports. So imports are very much similar to Java imports or C, C++ includes, which is essentially importing or including the necessary libraries that we'll be using. And as you can tell from the name, we are essentially importing libraries required for Mininet. So Mininet has a Python library. From the Python library, we are importing different classes that we'll be using. For instance, Mininet class, that's the most fundamental class. that is required for creating the network itself. Then we have classes for nodes and controllers, for adding switches, hosts, and controllers to our topology. Then we have classes for link types. For instance, say we want to create a link with some bandwidth capacity or some delay. Then we use this TC-link class from Mininet's library to create such links, right? So now let me go through some of the steps of how we create a network in Mininet and add more hosts and switches to that, and then we'll try to run this example in our virtual machines. So the first step is actually to create a network. Create an empty network that doesn't have anything in it. There is no host, there is no switch, and also there are no links for sure. So we are essentially creating a Mininet object and specifying for the future hosts and the links, what kind of links we will be creating in future, what kind of hosts we'll be creating in future. In this example, we are saying that, okay, the hosts will be creating in future, we should be able to limit their CPU. If we don't mention like this part, for instance, if we take this thing out from here, we'll be creating default hosts that we have been seeing so far, right? We keep it here, we'll be able to create hosts where we can limit the CPU uses of the hosts. Similarly, with this link parameter, we are saying that this is the type of link we'll be adding in future to this network object, right? So these are like TC links or traffic control links, where we can emulate bandwidth and latency and so on and so forth, right? So that's the first step. We created an empty network. Now, since we have an empty network, let's try to add more stuff to it, right? So let's first add some switches to the network. Let's create some switch instances, which is the next, statement. So what this statement is essentially doing is, the important part here is net.addSwitch. This function call. So when we have this network object, right? So this network object has a function called addSwitch. We can just call this function and keep adding switches. As a parameter, we pass the name of the switch. So this is a Python magic that is actually running a loop and iterating over these three elements, S1, S2, S3, these three strings, and creating a switch for each of the names. This can be written in a more elaborate way. This is just here for a concise representation. But anyway, for the time being, just stay with me. Let's go to the focus on the features of the APIs. So that's one thing. So now we added some switches to the network. Similarly, we can create network hosts and add the host to the network with this add host method, right? We give the host a name, and since when we created the network, we said that we should be able to limit the CPU of the host, we also specify a parameter here that, okay, what is the maximum cap for these hosts? 0.1 means 10%. So the CPU will be capped at 10% for the hosts. All right. So we added the switches, we added the hosts, and now what we need to add is a controller. Okay. So for controller, we're adding a remote controller. So a controller running at some IP address and some port number, right? So this is how Mininet SDN works. You add the switches. You can either skip the controller, then in that case we have to manually configure the switches later somehow to install the rules. The other option is to start with the controller at the beginning. So we are creating a controller object. So remote controller is a Mininet API that creates a controller object, specifying the IP address and port number where the controller is running, and then adding it to the network. right? So far, we started with an empty network, added 3 switches to the network, added 3 hosts to the network, and also added a remote controller in the network. All right, this is what we have so far. Okay, any questions? Are we good at this point? Other schools? All right, okay. Okay, so many thumbs up, so moving forward. Now let's add some links. So the network object has this method called add link. So with this method, we'll be now adding links to our network, right? So for link, what we need to specify are the endpoints of the link. So the endpoints would be the endpoint objects here. So if we go to slide 25, as you can see, when we added the switches, it actually returned an object reference to the switches as well. And we are holding the object reference at S1, S2, and S3. It's like creating a new object in Java or C++ and having the reference or pointer. Then when we're adding the links, we're passing the reference to the objects as well. At the same time, specifying some parameters for the links. Because now we are creating a traffic control links, right? So we can specify a bandwidth parameter and a delay parameter. So specifying these parameters, they have the same keyword as the CLI. So we use DW for bandwidth and delay for delay. And in this way, we are adding links to the network. So what we have now is something like a triangle. 3 switches, S1, S2, S3. You can see, if you see here, when we are adding the links, adding links between S1 and S2, S2 and S3, and S2 back to S1. So essentially creating a triangle of switches, right? A triangle topology, which is not possible to deploy with Mininet built-in topologies because it doesn't have this kind of topology built in. But this is just an example. So now we have the switches connected to each other. We have the switch topology, but the hosts, they are not connected to the switches yet, right? They're still isolated from the switches. We take the hosts and put a link between switch and the host. So connect H1 with S1, H2 with S2, and H3 with S3. We're doing here in this loop. We are connecting all the hosts with all the switches. So at this point, what we have is we actually have a network topology where we have put all the connectivities in place. Put the switches, the hosts, the links between the switches, links between switches and hosts, right? We have the network topology. So once we have the network topology, and then what we do is we start the switches. And after that, we start the network itself. So starting the switches is essentially saying that, okay, here's switch 1, then start with this controller. And that's what we're doing here in the API call, right? We're taking a switch from the list of switches and invoking the start method of the switch, specifying the controller, right? If you look at C1 here, so C1 is the controller object that was created on slide 25, right? We're passing a reference to the controller object here. So starting the switch, all the switches now, and specifying that, okay, this is your controller, connect to the controller and just boot up. Switches are boot up and the network is now started. So now at this point, we have a network with switches and hosts and links and controllers that is up and running, right? So this is how we can deploy a network topology, like a custom network topology using the Python API. Now, once we have the topology in place, is like from the Python API, we can actually play traffic inside the network. They do measurements like bandwidth measurement or delay measurement, so on and so forth. So for that, the rest of the code actually does the measurement. So what we're doing here is measuring the bandwidth between host 1 or 2, most likely, that we'll see in the next slide. So if you remember, we use this iperf command from Mininet CLI, right? And that randomly picked 2 hosts and did a bandwidth test in between the hosts, correct? So iperf by itself is a tool. tool where what you can do is you can run an iPerf server on a host and the iPerf client on another host and tell the client to do a bandwidth test with the server. This is actually how it works. So Mininet actually did a wrapper around this iPerf to do this bandwidth test without specifying any parameter at all. So here we are actually running an iPerf server on host 1 by executing this command. So .cmd, this is a method available at host that executes a command on that host. So it will run this iPerf command on the host and in the server mode. Then when we go to the next slide, slide 27, we take host 2 and run another iPerf command in a client mode. When we run an iPerf command in the client mode, we tell the client that, okay, run as a client mode and that is your server IP. Do the bandwidth test with the server IP. This line is essentially building that command, getting the IP address of host 1, specifying it as a server IP, and running it for 2 seconds. And this whole line is just doing some output processing and taking the exact bandwidth number out. And we're printing it here. So to summarize, what we did was first start with an empty network, add switches, add the host, add the links, boot up everything. Once everything is boot up, then we write our code for doing the experiment. Right? In this case, our experiment is running iPerf between two, like a pair of hosts, just a pair of hosts. All right. So let's try to execute the Python script and see if it works or not. All right. Let's go to the VM. I should have copied the Python script in the VM. I think I forgot to do that. So we have to copy paste from the slide, and fingers crossed that it works. Hopefully it will work. All right. Let me open Gedit. I have to copy the script there. Yeah, one thing you have to remember about Python is that it is space sensitive because you have noticed it doesn't have any notion of braces to define blocks. So code blocks, they are defined by these spaces. So here, like if we put it like put a mode, like a one space mode, it actually represents a different code block, and it will not compile or interpret properly. So try to make sure that the spaces are proper. Okay, so I just copied the code that was in like across 3 slides here. Let me just save it somewhere. Okay, let me just save it in the main, like in the home directory called mntest.py. Save. Okay, since I gave it an extension, now we can see colors. All right. So while copy pasting the code, just make sure that the alignment is not broken. Again, Python is space sensitive. If the alignment is broken, you'll see errors. So we have the code. We'll execute the code. Now, there's one thing, right? So the thing is, we created a remote controller that is running on a IP address and port number, but we haven't really deployed the remote controller yet. When we were deploying Mininet, Mininet was starting a controller by itself, but when we're doing it from Python API, Mininet will not do that. So we need to start like a controller, like an SDN controller that will work with this code. So let's get back to the CLI. Okay, so first of all, clear all mininet instances, quit them, close them, close all the mininet instances. It is closed, so no mininet instance is running. In the home directory of the virtual machine, there is a directory called Floodlight. So Floodlight is one OpenFlow controller, like it's one of the early OpenFlow controllers. It's Java based, open source. So let's run Floodlight. I think I have the command here in the slide. Go to slide 22. So slide 22 has the command to run Floodlight controller. So let's copy the command and run the controller. All right, so when you run the controller, it will show some output and stall at some point. So everyone, please try to run the controller on your laptops as well in the virtual machine. Make sure it is running before we execute our Python script. Now, let's go to a different window now and try to execute the Python script. So we have the controller running. Python script and see what happens. The way we run it is that Python, and we provide the name of the script and syntax error. Okay, all right. Syntax error on line 14. On ASCII character. Okay. What? Let's remove line 14. Probably when we copied. So this is line 14. Create the network host and all this stuff. Most likely when we copy it, there is some UTF ASCII conversion issue. Just remove the line, save it, and try to run again. Sudo. Sorry. Since we are essentially executing like mininet under the hood, we need to run it as super user because we're creating all the switches and links, and that requires super user privilege. So run it as sudo, and it is adding the links. So far, so good. Starting a controller, starting the switches, but something failed. Okay. Right. So our controller threw an exception. Good. So quickly check one thing. If there is something else in the system trying to interfere. Okay, so there are a few switch instances. So let's try to clear up everything. So if we run this command mininet mn with -c, it will clear up all the residual switches and links that is in the system. So let's clear them up and see if there is still something around or not. Okay, so there is nothing. Let's check another thing, if any other controller is running and trying to interfere or not. So when I run this command, it will actually show all the processes listening on different ports. Don't see anything running on the controller port. Okay, so far so good. Let's try to run everything again. Okay, so first the controller. First run the controller. So the controller is running and listening to port 6653, which is the port that we used, I hope. We created the controller 6653. Yes, that's the port we used. Okay, so let's try to run the script again. Adding the stuff. Okay. Okay, so there was no error this time. All right, so if you're like facing problems, so first try to clean up if there is anything that was left from previous mininet run by running mininet -c. After cleaning it up, rerun the controller and run the script again. So this time, can everyone see this output? While it reports a throughput between two hosts. Can everyone see that on their virtual machine? Yes? No? At other schools, were you able to execute the script and see the output, or are you facing like problems? Okay, got thumbs up from UFT and so are we all on the same page here?
No, some of us still running.
Sorry, so I'm asking is what I'm asking is so were you able to see this output on your virtual machines as well?
Yeah.
Yes for everyone. Okay, all right. So if everyone was able to see this output on their VMs, this means that the script successfully executed. So this is an example of how we can use the Python API to create custom topologies, like deploy custom topologies. Deploy custom topologies, as well as, since it's Python, it's a programming language, we can also deploy custom traffic matrices, right? This is an example of deploying like just a traffic, like plain traffic between a pair of hosts. But you can imagine, if you have like complex traffic matrix pattern, you can also play that as well with delays to make sure that you can emulate traffic arrival and departure, this kind of behavior as well. All right. So I think that's pretty much it for the tutorial. Just to make sure I did not miss anything. Yeah, so that's pretty much it for the tutorial. So the main objective was to get familiar with the Mininet and OBS. We looked at how we can create topologies using Mininet, like just from CLI, and also from using like a Python API, like some custom topologies, run traffic with that. At the same time, we used OBS CLI tools to see the internals of the switch, add flow rules, see statistics, see the capabilities and whatnot. So that will conclude our lab session today. And I think there is an like lab exercise part component to the course as well. So the lab exercise will be probably posted later sometime, and there will be a due date as well to submit. So the instructions to how to submit, how to do the exercise, everything will be on the post. So yeah, that's pretty much it from today's session. Any questions, concerns?
I have a small question from the code.
Sorry, can you please repeat? Your voice actually got cut off.
I have a small question from the code.
Yes, go ahead.
How do I configure the link between switch and controller?
How do you
configure the link between the switch and controller?
How do you configure the link between the switch and the controller?
Yeah.
Okay, all right. So what happens here is that the controller and the switch, they maintain a TCP connection in between them that is out of band of the main OpenFlow network. So when you create the links and add them to the network, that is actually adding links to the OpenFlow network we're creating, right? The SDN. But the communication between the controller and the switch, that is taking place out of band. It is not going through the same data plane as the OpenFlow network. Does it answer your question? So you don't need to actually do custom modification on that. It is using the default network stack for this communication.
Yeah. Okay. Yeah.
All right. Any more questions? From here, Waterloo, any more questions? Okay, so if there are no more questions, then I guess that's the end of the lab session today. And thank you very much all for attending. Right? See you next week.
Thank you very much.
Yeah,
see you.
Bye.
Video.